Hello, my name is Nick Kinzel, and this is Amber Welsh. And our project is on the Big Bang Theory, and specifically measurements that were taken very recently that help us identify precise reactions and the rate at which those reactions occur moments after the Big Bang.
First off, we're going to start by talking about the Big Bang Theory, what that is, and exactly what it means.
The first thing the Big Bang Theory is it's a TV show. Oh, please. Oh, no.
Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids. Math, science, history, unraveling the mystery that all started with a Big Bang. Hey!
But in all seriousness, the Big Bang Theory isn't just a TV show. When we ask ourselves how the universe came to be, there isn't exactly a perfect answer, but there is a widely accepted theory throughout the scientific community. And this is exactly what it is. What happened 13.8 billion years ago? Basically, everything that existed was in a small ball of infinite density. And that is called it started to expand and just kept expanding and expanding and expanding until it became the universe as we know it. But it still could be expanding. We don't know for sure.
So there were a couple problems with the initial Big Bang Theory that was proposed around the 1920s or so. One of the problems with that was the implications of the general relativity equations with an object that had an infinite density, and people were not very comfortable with that at all. And yeah, the general relativity equations had no way of describing such a singularity. The other problem was that with the singularity and the expansion that was theorized to have occurred, doesn't quite match up with our current cosmic background radiation readings. So those were a couple of problems with the original theory. To counteract this, there was a physicist in the 80s named Alan Guth who published an explanation for this. And basically what he said was what we thought was a singularity was actually a finite but very, very highly dense ball of matter, but finitely dense. And what he said was what we thought was that singularity had already been expanding very rapidly. And when it started slowing down, that's what we considered to be the Big Bang. And so basically you have two rates of expansion, and the rate of these expansions is largely unknown. And what happened around this time was only theorized.
Next, we're going to look into some of the background of the science in the experiment that we're talking about. First off, we're going to talk about deuterium and what it is and why it's important. Deuterium is a form of hydrogen that consists of one proton and one neutron. You'll see in the bottom right-hand corner here that we have a normal hydrogen atom and we have a deuterium atom. And the first three elements, such as helium and lithium. So that's basically right after the Big Bang had just happened. Deuterium has all these amazing reactions to form all of our elements that are so important in building the universe. And what deuterium remains unlocks the answers of how our universe was created. the deuterium reaction that these scientists are studying in their laboratory in Italy, which is underground, so cosmic rays don't interfere with their experienced protons at deuterium in order to determine the rate at which it fuses, so that we can figure out exactly how it's forming all of these elements to create the universe. This rate can help us find information for the first few minutes of cosmic expansion. And that's important things such as density of protons and neutrons and how quickly they can separate.
So the key to the deuterium reaction is these the scientists really wanted some tangible piece of physical evidence that supported the details of the Big Bang theory, because the theory was a lot of speculation and hypothesis, but there wasn't really anything physical to show for it. So that's what this was attempting to provide, and the goal is to mimic the cosmic background radiation that has already been established, so that you have something that a reaction that you can do, and you get the rate of the reaction, you get how fast it goes, and you get something that looks like the cosmic background radiation that we've already observed, that can prove that this is something that would emulate the Big Bang theory sufficiently. And not only did the experiment ended up emulating the cosmic background radiation that we've already recorded, but it actually looked like it supported a theoretical measurement of cosmic background radiation appears 400,000 years theoretically in the future. So that's very exciting. And here's a chart of the that incorporates the data that was just published. And as you can see, there's a lot of other measurements on here. There's the TISMA from 2019, which looks like it agrees with the measurement that was just taken, but you can see the error bars are very large. It was largely imprecise. And all the way back here in the 60s, there was a yellow measurement that was taken. And the error bars are smaller, but it doesn't look like it quite is very accurate. But the measurement that was just taken is this red one, and as you can see, the error bars are very small, and it actually splits the difference very well between all of these other measurements that were really taken, and it was very precise. So that's an exciting measurement. And there's a lot of implications to this measurement, a lot of exciting effects of knowing this stuff. One of them is, of course, knowing what happened moments after the Big Bang. You can use this experiment to help determine the density of the primordial matter that just before it exploded into what we now know as the universe. And we also, from that, we can tell how quickly the initial expansion occurred, which leads to a lot of other very cool implications, because we can then determine what the universe is going to look like in the future. We use this and our knowledge about how the quote-unquote curvature of the universe works. And what that means is the expansion of our universe, it's either speeding up or it's slowing down. And that is basically what determines what the curvature is. And we can use this rate to determine whether or not it's going to accelerate or whether or not it's going to slow down and reverse into sort of a big crunch. The last thing that we get from this experiment is simply just the joy of having more knowledge about the universe. Because we as humans are naturally curious beings, and we're going to need to know this stuff if we're ever going to leave Earth permanently. We're going to need to know how space expands or contracts. And the last really important thing that we get from this is we get to know that quote-unquote singularity before the Big Bang exploded. General relativity had a real problem with that, but as we get to understand it more, we get to couple general relativity with quantum mechanics and unify them together, which is a really important concept for physics moving forward in the future. And here's our works cited sheet.